talk about the sequential circuits. So what we are going to see in the sequential circuit is that first of all we are going to compare sequential and combinational circuits. So the difference between combinational and sequential circuit is here. In combinational circuit, we do not have any of the present output dependent on any of the past history. Here the output at any instant is only dependent on the present input variables. There is no requirement of any memory unit and they are relatively faster. Combinational circuits are relatively easy to design. What happens in sequential circuit is that in sequential circuit, output at any instant is dependent on the present input as well as on the present state. So here we see that past history is also important and the memory is required to store the past history of the input. They are slower and comparatively harder to design. So the logic circuit whose output at any instant of the time depends on present input as well as on the past output are known as sequential circuits. Here there is a feature is that the output signal are fed back to the input side. So there are four main subtopics in the sequential circuits. The first one is the latch, second one is flip-flop, shift registers and counters. So what is a latch is that latch is just a combination of two NOT gates which are connected end to end or in series connection. It is a bistable logic circuit and has a basic memory unit. Here the input is stored and keeps on moving until we change it with another logic. So latch memory unit will store 1 bit of data. 4 bit of data is called as nibble and 8 bits of data is called as byte. So if we want to change the data stored, then it is not possible because once we store something in the NOT gate, we have to apply another logic either high or low, which is different from the previous one to change the stored value. But at the same point, at the same time, we cannot have two different logic values. So we cannot change the whatever information that we have stored in a latch. So modify it with a NAND gate. So this is how the modification looks like. And this is a NAND gate and another we are seeing just right side of it is a NOR latch. So this is NAND latch and NOR latch where we have used two NAND gates and two NOR gates respectively. Here we are seeing that there are two inputs and two output ports in which the two output ports are complement of each other. If we denote Qn as a previous state, then Q of n plus 1 will denote the present state. So this is the design of the NAND latch and here this is the truth table. So what we have done in the truth table that we have taken S and R as the input and Q bar as the output. So for the first combination of S and R we have taken 0 0 and for Qn we are alternatively taking 0 and 1 as a combination. So here in the first case when S is 0, R is 0 and Q of n is 0, we are getting the output as Q of n plus 1 is 1 and Q of n plus 1 bar is also 1. These two should be complement of each other, but they are not so. So they are not working condition. In the second case, when S is 0, R is 0, and Q of n is 1, again Q of n plus 1 is obtained as 1, and Q of n plus bar is 1. So again this is not working. In the third case, when S is 0 and R is 0, Q of n is 0, we get the Q of n plus 1 value as 0, and Q of n plus 1 complement is 1. So here in this case, this is the working state. Now consider the fourth case. When S is 0, R is 1 and Q of n plus 1 is 1. Again these two outputs are not complement of each other, they have the same value. So this is not working condition. In the next case when S is 1 and R is 0, we have Q of n as 0. Here this is the working state and in the subsequent states these all are working conditions. So here we have 5 working conditions and 3 not working conditions in case of a NAND latch. We can reduce the table of a NAND latch in the given diagram. As per the reduced table, when S is 0 and R is 0, we have consecutively divided into 4 cases when S is 0 and R is 0, when Q of n plus 1 comes to out P as X. So this is invalid state. And when S is 0 and R is 1, Q of n plus 1 is 0 and this is reset state. When S is 1 and R is 0, Q of n plus 1 is 1 and this is set state. When S is 1 and R is 1, Q of n plus 1 is n and this is hold state. Now we can similarly talk about the NOR latch where we have simply replaced the NAND gates with the NOR gates. Here S and R are again taken as the input gates and Q bar are the output. So in the first case we have again designed the truth table like this we have previously did in the case of NAND latch and now we have reduced the truth table. So in the reduced table what we are going to see is that when S is 0 and R is 0 we get Q of n plus 1 as Qn. So it is the same state that was present in the previous state. So we can say that this is hold state or the memory state. In the second case, when S is 0 and R is 1, Q of n plus 1 is 1. This is called as the set states. In the third case, when S is 1 and R is 0, we can say that Q of n plus 1 is obtained as 0. So this is reset state. In the next case, when S is 1 and R is 1, we get Q of n plus 1 as x, which is don't care.